coming to the next unit, but before that we have some more bigger or smaller units that we talk about the time. Like we said, solar day. So solar day is the time taken by Earth to complete one rotation about its own axis. So say you are on Earth, so sun is here, and next day when the sun will be here, just on the same position above you, you will say it's a solar day. Yes, it is not because the sun has moved, it is because we have moved, the Earth have moved. Sidereal day. It is the time taken by Earth to complete one rotation about its own axis with respect to a distant star. So with respect to sun, how much time Earth take to revolve about its own axis? This is solar day. With respect to a far off star, how much time does the Earth take to revolve complete about its own axis? It's a sidereal day. One solar day is 24 hours. And one sidereal day is 23 hours, 56 minutes, 9.5 seconds. Then a solar year, time taken by the Earth to revolve once complete about the sun. Tropical year, the year in which there is a total solar eclipse. Tropical year, leap year, then when you have Feb of 29 days instead of 28 days. Lunar month, it is 27.3 days, one lunar month. Time taken by the moon to complete one revolution about the Earth in its orbit, 27.3 days. And shake is the smallest unit of time, 10 to the minus 8 seconds. So that's how there are various units of time. They are into practice in different situations at different part of physics. Then we talk of another SI unit, and that is SI unit of current, and which is 1 ampere. Now how 1 ampere, how the standard definition of 1 ampere is given? In fact, it is based on the fact that if we take two wires carrying current, two infinite long wires, and they are carrying current in the same direction. If they are carrying current in the same direction, there is a force of attraction between them. If they carry the current in opposite direction, there is a force of repulsion between them. So if there are two wires that are carrying current in same direction or opposite direction, and they are kept by 1 meter, they are kept 1 meter apart, then a force of attraction, and if the current is 1 ampere, 1 ampere is that current which develop a force of attraction between them of the order of 2 into 10 to the minus 7 Newton per meter. So for every meter length of these two wires, there will be a force of attraction of 2 into 10 to the minus 7 meter, Newton per meter. So we can define 1 ampere as that current which when flow in two parallel wires produce a force of attraction or repulsion of 2 into 10 to the minus 7 Newton per meter length of each wire. And that's how the standard definition of current is there, and it is when they are kept in vacuum. Now moving ahead, so we have defined 4 units. We have defined kilogram, we have defined 1 meter, we have defined 1 second, then we have defined 1 ampere. Now going to the next one, and it is temperature. SI unit of temperature, 1 Kelvin. So this is the SI unit of temperature. It is 1 by 273.16 of thermodynamic temperature of triple point of water. Now what is triple point of water? There is a state at which temperature the water coexists in the form of ice, steam and liquid. And it happens at 273.16 Kelvin. At 273.16 Kelvin, the water coexists in the form of liquid, ice and steam. This is called triple point of water. And 1 Kelvin is 1 by 273.16 of it. of that temperature. Yes, when we are talking of temperature, we have three different temperatures that we generally talked about: Kelvin, degree Celsius, and degree Fahrenheit. So 1 Kelvin is actually 1 degree Celsius. So Kelvin and degree Celsius, the gap, 10 degree Celsius change mean 10 Kelvin change, they are the same thing. Similarly, 1 Kelvin is 1.8 degree Fahrenheit. It is generally used in United States, but the standard unit of temperature we use is at Kelvin. Yes, if ice melt at 0 degree Celsius and water boils at 100 degree Celsius, this is 0 degree Celsius is 273.16 Kelvin and this is 373.16 Kelvin. So this is how they are related to each other. Standard unit of temperature, we use Kelvin, and change of temperature 1 Kelvin is equal to 1 degree Celsius. Then let's come to SI unit for visible light. Now LED is used everywhere. So we want to measure this visible light because in all those instruments, in all those lamps which produce light, they also produce heat energy as well as visible light. So we want to just measure visible light. So 1 candela, it is represented as CD. Candela is the unit of visible light or luminous intensity. Luminous intensity. So 1 candela, amount of visible light emitted by a source per unit solid angle in a specific direction is luminous intensity. How much a light source per unit solid angle it emits the light, visible light, that is the definition of luminous intensity. And 1 candela is the SI unit of luminous intensity, which is a unit for amount of visible light by a source. And if we are taking the definition, 1 candela is the luminous intensity in a given direction of a source that emit monochromatic. Monochromatic radiation means one wavelength radiation, one color radiation of frequency 540 into 10 to the power 12 Hertz, and that has a radiant intensity of 1 by 683 watt per steradian in that direction. So this is the standard definition of 1 candela. Now let's define this another unit, which is SI unit for quantity of matter, 1 mole. In fact, if I take, like in this carbon C612, its atomic mass is 12. So we can define that 12 gram of carbon will have 6.022 Avogadro number into 10 to the power 23 atoms, and it makes 1 mole of it. So this is the basic concept. From atomic mass we can make out 12 gram of carbon will have Avogadro number of atoms in it and will make 1 mole. Similarly, 1 mole of H2O. So 1 mole of H2O, how to get? For H2O, the atomic mass will be 18. So 18 gram of H2O will have 6.022 10 to the power 23 molecules of it, and it will make 1 mole. Similarly, 1 mole of NaCl, sodium chloride, its 1 mole will have 6.022 into 10 to the power 23 molecule of it, and it will make 1 mole. So I hope you have understood the concept of 1 mole. Now from here I can move to these two supplementary units, radian and steradian. If we are talking of plane angle, angle in 2 dimension. So angle in 2 dimension will be theta is equal to arc by radius. So theta is equal to arc by radius, and for its unit, it's radian. Otherwise, unit of arc is also length, meter. Unit of radius is also length. So it seems to have no unit, meter by meter, no unit. But here we represent it as radian. Similarly, in case if we are talking in 3 dimension, like think of a ball, how much one area on the surface of ball angle, how much angle it will be putting at the center. So it's going to be a solid angle. So solid angle, like this is a ball and I take one area of it, how much angle does it put at the center? This is called solid angle. Now solid angle is represented as omega, like plane angle is represented by theta, solid angle is represented by omega, and it is area divided by r square, and its unit is steradian. So radian is the unit of plane angle, and when it's a solid angle described by an area on the surface of a spherical body, then its unit is steradian. So that's how we use 2 supplementary units in SI system. So children, now we are clear that SI is finally used internationally and accepted internationally as a system of unit, the best system of unit. What are the advantages of SI system? One advantage we have understood that it covers all branches of physics, with its 7 fundamental units and 2 supplementary units. Coming to other advantages of SI system, first is it's a coherent system of unit. Now, what do we mean by saying coherent system of unit? Coherent system is a system where all derived units can be obtained by simply multiplying and division of fundamental units. No numerical values to be added. For example, if I'm saying for length, the unit is meter. For area, the unit is meter square. For volume, the unit is meter cube. For density, the unit is kilogram per meter cube. So all these derived units are obtained by simply multiplying and division of fundamental units. No numerical values to be added. For example, velocity. So it is meter per second. Distance per unit time. For acceleration, it is meter per second square. They are all derived units. But if I am talking of a system where the unit of velocity would be 1 kilometer per hour. So any system where the unit of velocity is say 1 kilometer per hour, it means, and I want to convert it using the smaller units, 1000 divided by 3600 meter per second, I will get 1 by 3.6 meter per second. Here, for getting this velocity, I have to introduce this numerical value. So this derived unit of velocity in terms of fundamental unit has a numerical value to be added. It's a coherent, non-coherent system. But here, for velocity, the unit is meter per second. For acceleration, the unit is meter per second square. For force, the unit is kilogram meter per second square. No numerical values to be added. It's a coherent system of unit. The second advantage, SI is a rational system. When we say rational system, it means there is one unit for one physical quantity. For example, we take the case of energy. If we say in M case, we have mechanical energy. Let's talk mechanical energy. So mechanical energy, we represent its unit in M case is joules. Unit of heat energy is calorie. Unit of electrical energy is watt hour. It's not a rational system. But in SI, if we are talking in SI, for all energy, the unit will be joules. The unit is going to be joules only. Here, I'll give you some more detail. Should we call it joules or should we call it joule? So my answer is should be called as joule rather than calling it joules. Third is SI is a metric system. It's a metric system. What do we mean by saying it's a metric system? It means multiple and some multiple are expressed as power of 10. Like if you say 1 kilometer, it is 10 to the power 3 meter. If you say 1 centimeter, it is 10 to the power minus 2 meter. All bigger and smaller multiple are just multiplied, just represented in the power of 10. And on the other hand, you take this, 1 foot is 12 inches in FPS system. So it's not a metric system. Now let us discuss the fourth advantage of SI system, and that is SI is absolute system of unit. It means SI system does not use acceleration due to gravity in its unit system. For example, first I will take the example of MKS and CGS where we are using G, acceleration due to gravity in this unit system. In MKS, if you have 10 kilo weight of, you have a 10 kilogram mass, weight of 10 kg mass would be written as 10 kilogram force. This is called gravitational unit of force. Or its other value is 10 into G, which is 10 into 9.8 or 98 Newton. So the weight of this 10 kg mass, weight means force, force by earth on it. So weight of this 10 kg mass is either written as 10 kg force, this is gravitational unit of force, or it is 98 Newton. Similarly, in CGS, if I have a 10 gram mass, if I have a mass of 10 gram, its weight of 10 gram mass would be written as 10 gram force. This is gravitational unit of force in CGS. Or the value of G, or it will be 10 G, which is 10 into 980. So it is 9800 dyne. So in CGS also, it's not an absolute system because we have got two options for describing force, either in gram force or in dyne. Here I have got two options for describing weight in MKS, either 10 kilogram force or 98 Newton. But in SI, it is not like this. In SI, it's an absolute system. The only unit of force is what? Kilogram meter per second square. The only unit of force is kilogram meter per second square and nothing else. So that's how SI is an absolute system. There is one unit for one physical quantity and it doesn't keep on changing. Now let's learn some interesting thing that we should follow while writing different SI unit. More you put them into practice, lesser mistakes you will be doing while writing these units. The first one is the symbol for the unit named after scientists are usually the first initial letter. For example, you are writing the unit of say somewhere 100 Newton force. So you should call it 100 Newton, like this. If you are writing, say, 2000 joules of energy, so you should write 2000 joule, like this, capital J. If you are writing, say, somewhere 2 ampere of current, it means you can also write it 2 ampere of current. So here, whatever units are after the name of the scientist, if you are just representing them in a single letter, then it has to be capital 1. Second, the unit in the name of scientist is not written in capital initial letter. So whenever you are writing just the name of the scientist, like 100 Newton, so if you are calling it 100 Newton, this is incorrect. It has to be Newton, the small letter initial. Similarly, 2000 joule, so it cannot be 2000 capital joule, like this. It should not be starting with the capital letter, it is starting with the smaller letter. Like 2 ampere, so it cannot be 2 ampere. It has to be small a, 2 ampere, like this. So when we are using the capital letter, it is only when you are just using one letter. And if you are using the full name, then start with smaller initial, smaller letter. Let's come to this third point. And point number 3 is, small letters are used for symbol of all other units. So for all other units, small letters, except those units which are after the name of the scientist. For example, 500 kilogram force. So it cannot be kilogram like this. It has to be 500 kg or small kg. If you are talking of, say, in the same way, if you are talking of meter, say 2 meter, so it cannot be 2 meter to be written like this, or 2m. It cannot be 2m, it should be 2m, 2 meter. So all other units are represented in small letters. And now coming to m itself, m is for meter as well as m is for milli. Now question is, in what situation it should be used as a milli and in what situation it will be used as a meter. So here, when we are writing Newton meter, here, say the unit of work, Newton meter. So here, it should be written as Nm, like this. So meter, whenever it is afterward, then it is meter. And in case if it is millinewton, the smaller unit of force, or 10 to the power minus 3 Newton, then we should write it Mn. So when this M is prior, it is milli, and when it is later, it is meter. This is particularly for M, small m. And another point is, which is also important, the units do not have plural form. So I should call it 10 Newton and I should not call it 10 Newtons. I should call it 100 joule. I should not call it 100 joules. And also, the last point, the full stop is put between the symbol of, is not put between the symbol of units. That is Newton dot meter, it is not acceptable. Newton meter is acceptable. So I am not going to put full stop between these. So it is just Newton meter and full stop. So that's how we are going to keep all this in our mind when we are representing different units, writing different units anywhere. It's really interesting. And if you can recall, in the beginning, I have introduced how to use the abbreviations for very small or very big units. For example, if I'm talking of meter, say 1 meter is a standard unit in SI of length. But in a situation, I may have a smaller unit like decimeter. So this is 10 to the power minus 1 meter. So 1 decimeter is 10 to the power minus 1 meter. 1 centimeter is 10 to the power minus 2 meter. 1 millimeter is 10 to the power minus 3 meter. 1 micrometer is 10 to the power minus 6 meter. 1 nanometer is 10 to the power minus 9 meter. 1 picometer is 10 to the power minus 12 meter. Femto or 1 Fermi meter is 10 to the power minus 15 meter, and atto, that is 10 to the power minus 18 meter. So this is decimeter, this is centimeter, this is millimeter, this is micrometer, this is nanometer, this is picometer, this is Fermi or femtometer, and this is attometer. So they are the smaller units, abbreviations in the power of 10 for smaller units. Similarly, in the bigger unit, 1 decameter, DMM, that is 10 to the power 1 meter. 1 hectometer is 10 to the power 2 meter. 1 kilometer is 10 to the power minus 10 to the power 3 meter. 1 megameter, mega is capital M, 10 to the power 6 meter. 1 gigameter is 10 to the power 9 meter. They are all in capital. 1 terameter is 10 to the power 12 meter, terabyte. 1 petameter is 10 to the power 15 meter. 1 hexameter is 10 to the power 18 meter, like that. They are the bigger units. And remember, all these bigger units, mega, giga, tera, peta and hexa, are in capital letters. And it is not only for meters, it is also for gram or maybe kilogram. Similarly, I can say 1 decigram is 10 to the power minus 1 gram. 1 centigram is 10 to the power minus 2 gram, and like that. Similarly, in 1 decagram is 10 to the power 1 gram. So like that, you can always introduce these abbreviations with any of the physical quantity unit, and you can represent the bigger or the smaller unit in the multiple of 10. Like here, the unit of resistance. In current electricity, you have studied resistance. The unit of resistance is ohm. Ohm is represented by omega like this. So 1 mega ohm, capital M, 10 to the power 6 ohm. 1 milliampere is 10 to the power minus 3 ampere. 1 kilometer is 10 to the power 3 meter. So like that, these abbreviations, they can be used everywhere with every unit to represent multiple of 10, the smaller units or the bigger unit. So we'll keep them in mind. 1 nanometer is 10 to the power minus 9 meter. 1 nano ohm is 10 to the power minus 9 ohm. 1 nanogram is 10 to the power minus 9 gram. So it's like that. It can be used, these abbreviations can be used with every unit to show them the bigger or the smaller values.